So with that, we've successfully predicted our bounding box, completing this step. Of course, while we just walked through this process for one grid cell, the same calculations are performed for all 6,300 grids. Ultimately, the grid with the highest class score will determine the final bounding box. And that brings us to our next step, analyzing class scores. Let's take a look. So now, if we focus on the class predictions for each grid cell, what we do is apply the sigmoid function to each raw logit. This maps the values to a scale from 0 to 1, representing the likelihood or probability of a particular class being present in that grid cell's prediction. Since this model was trained on the COCO dataset, which contains 80 different object classes, each grid cell has 80 class scores, one for each possible object type. We can also print these values for a specific grid cell, such as grid 6150, and take note of this value, 0.88, which corresponds to the score for class index 2. Now, at the 15 by 20 feature level, we can visualize which grid cells get activated for different classes. For class 0, person, no grids are activated. The same happens for class 1, bicycle class. However, for class 2, which corresponds to the car class, we can see that 10 grid cells get activated. Each of these activated grid cells has a bounding box prediction, as we saw earlier. But ultimately, the grid cell with the highest class score will determine the final prediction. By simply looking at these values, we can see that the brightest yellow represents the highest class score. And if we check whether any other classes get activated, the answer is no, only the car class is detected. Now, if we overlay the input image with the car class feature map, we can clearly see that all these class scores align with the car in the image. And in particular, the highest class score corresponds to grid 6150, the one we've been working with all along. So let's recap. Grid 6150 was the winner for the car prediction. Since it had the highest class score, its bounding box dimensions were selected as the final output bounding box for the car class. And spoiler alert, if we peek ahead at the final YOLO output bounding box, it should come as no surprise that it will match the annotated bounding box exactly to the pixel level. And of course, remember that 0.88 score for the car class, that gets recorded in the final annotated output as well. As a curiosity, while the grid prediction does not need to be exactly at the center of the bounding box, in most cases, grids near the center of the object tend to capture the strongest features. This often results in them producing higher class scores, making them more likely to be selected as the final prediction. For some people, this might be enough since we now have the class confidence scores alongside their corresponding bounding boxes. However, while we analyze these scores here for a deeper understanding, they are often not directly available until the end of the process. That's because the predictions typically undergo a confidence score threshold and non-max suppression, NMS, to eliminate redundant bounding boxes for the same object. To explore this further and continue through the YOLO detection pipeline, let's return to the code and start making our way back. We concatenate the tensors containing the bounding box coordinates, formatted as the center, x, y, width, and height, with the class scores. This concatenated tensor is then returned to the forward method of the detect class, where it is stored in y. From there, we return the tuple that contains y, as well as the list of tensors x, back to the predict once method. This effectively overrides the value of x with yx. Since we've now completed the iteration over all the modules in the architecture, the output is passed back to the predict method inside the base model class. We then return to the forward method of the base model, and once more to the forward method of the auto backend class. As you can see, we are returning, and returning. Here, inside the auto backend class, we store the results in y and continue processing. Since y is a tuple with a length of 2, the else branch applies, meaning we iterate over each element in y and process it using from NumPy. This function converts any NumPy arrays in y into PyTorch tensors, while leaving other elements unchanged, which is exactly what happens in our case. With that, we complete this class and return once again. This also concludes inference in the base predictor class, and we return once more. Now our final predictions are stored in pred, marking the completion of the inference profiler.